Now we shall discuss a new topic, solutions. Solution is a homogeneous mixture of two or more substances. That is, the definition of solution is it is a homogeneous mixture of two or more substances. So a homogeneous mixture of two or more substances is what is called a solution. A solution contains two components. The substances in the solution are known as components. That is, it is a homogeneous mixture of two or more substances, and these substances contained in the solution is known as components. Components are of two types. The first component is what is called a solute, and the second one component called a solvent. So it's a mixture of solute and solvent. It is a homogeneous mixture of two components. The first component is what is called a solute, and the second component is a solvent. The component in smaller quantities is what is called the solute, and the component in larger quantities is what is called the solvent. So if we take a solution, the component in smaller amounts is what is called the solute, and the larger amount is what is called the solvent, and the mixture of these two that forms a homogeneous mixture, and that is what is called a solution. Now we can look into the different types of solutions. See, substances exist in different states. Usually the three states of matter which are existing are gas, liquid and solid. These are the three ordinary forms of matter. So the solute and the solvent may be present in the gaseous state, liquid state or solid state, and hence there is permutation and only 9 permutation and combinations are possible. That is, a gas may combine with another gas, a liquid may combine with a gas, a solid may combine with a gas, or a liquid may combine with a liquid with a gas, or liquid with a salt, or the solid may combine with a gas, a solid may combine with a liquid, or a solid may combine with another solid. So altogether 9 types of combinations are possible in case of a solution, and we can look into the different types of solutions possible by the combination of the solute and solvent in gaseous state, liquid state and solid state. That is, types of solutions. Types of solutions, then solute, solvent. See, different examples of solutions are given here in the right hand side, and we can classify these types of solutions into 9 categories. 9 examples are also given, and each one refers to a combination in the gaseous state, liquid state and solid state. A gas may combine, that is, gas, liquid and solid. So a gas may combine with another gas. That is, an example is mixture of two gases. That is, oxygen is one gas, nitrogen is another gas. So a gas may combine with another gas, and that forms the first combination, that is gas and gas. Solute is a gas and the solvent is also a gas. Solvent is another. That is, gas and gas type is a mixture of oxygen and nitrogen is an example. That is one of the combinations. Then a gas may combine with a liquid. That is, liquid plus gas. That is, the liquid is chloroform and the gas is nitrogen. So here the solute is chloroform and the solvent is nitrogen. So a liquid in gas combination is given by the chloroform plus nitrogen. And the third one, solid in gas. Solid in gas. Example is camphor. Camphor is a solid and nitrogen is a gas. So a solid in gas combination is given by the example camphor in gas. So the solute and the solvent, the different combinations, in all these cases the solvent is a gas, whereas the solute is gas, liquid or solvent. Then other combinations. Here only a solvent may be in the liquid form. Then gas in liquid. Gas in liquid. That is, gas is oxygen, liquid is water. So it is a combination of gas in liquid form. Then liquid in liquid. Liquid in liquid. Ethanol is one liquid, water is another liquid. Ethanol and water are miscible in all proportions. Both are miscible in all proportions. So it constitutes an example of a liquid solute in liquid solvent, that is liquid in liquid combination, that is ethanol in water. Then a solid in a liquid. Solid in a liquid, that is solid is glucose, liquid is water. So a solid in liquid combination is given by the example of glucose in water. So that is a third combination. So in all these cases, the solvent is liquid and the solute is either gas or liquid or solid. Then in the third case, that is in the third combination possibilities, all cases the solid may be present as solvent, that is gas in solid. Gas in solid, that is gas is hydrogen, solid is palladium. Solid hydrogen gas is dissolved in, that is palladium absorbs hydrogen gas in all proportions. It has got a capacity. Palladium is a metal which is having a capacity to absorb hydrogen gas. So hydrogen gas absorbed in palladium is an example of gas in solid combination. Another one is liquid in solid. Liquid in solid. The liquid is amalgam of mercury. You know what is meant by amalgam? Amalgam is a solution of the substance in mercury. So any amalgam, that is amalgam of any substance dissolved in mercury is what is called an amalgam. And see here sodium is dissolved in mercury. So here mercury is in the liquid form and sodium is a metal. So liquid is amalgam and solid is sodium. So amalgam is a liquid and sodium is a solid. So liquid solid combination is given by amalgam of mercury in sodium. Then the last one, that is solid in solid. Solid in solid, that is copper metal in gold. See, 100 carat, 24 carat of gold is 10% pure gold. And if the purity comes down from 20 to 4 carats, the remaining is ordinarily added as copper. That is 22 out of 24 parts is constituted by gold and 2 out of 24 parts is constituted by copper. Then such a gold is what is called 22 carat gold. So 22 carat gold is an example of a solid combination, means the solute is solid, the solvent is solid. So it is an example of a solid combination. So these 9 types of possibilities are there and 9 types of solutions, that is 1 to 9. 1 to 9 types of solutions are possible, and these are examples. So these constitute the types of solutions. Now we can look into different methods of expressing concentrations of solutions. You know, a solution is a homogeneous mixture of 2 or more substances. Here we are going to limit our discussion to binary solutions, only, means having only 2 components, that is one solid and one solvent. In such cases, usually when we say solutions, the 2 components contained in the solutions, the solute is the component which is present in smaller quantities and the solvent is the component present in larger quantities. So depending upon the amount of the solvent and the solute, we have got 7 methods of expressing concentrations. These methods are, the one is what is called mass percentage, second one volume percentage, third one mass by volume percentage, fourth one parts per million. It is known by the short form ppm. Then the fifth one is what is called mole fraction. Sixth one molarity, and the seventh one molality. So these are the different methods of expressing concentrations, and in different situations we are using different methods of expressing concentration. We can take one by one. Now what is called mass percentage? As the name itself indicates, the mass percentage is the amount of the substance present, that is amount of the solute present by mass, that is amount of this out of the 100 parts. Usually percentage is taken out of 100 parts, so mass percentage is equal to mass of solute divided by total mass into 100. Total mass into 100, that is mass percentage. Then the similar is the case of volume percentage, that is equal to volume of solute divided by total volume into 100. It is also taken out of 100 parts. Then mass by volume percentage, that is mass of the solute present divided by volume of the solvent into 100 is what is called volume percentage. Mass by volume percentage, that is mass of solute divided by volume of the solution into 100 is what is called mass by volume percentage. Then parts per million. See, million is 10 raised to 6, that is number of parts of the solute present divided by total number of parts into 10 raised to 6 divided by total number into total number of parts into 10 raised to 6, that is parts per million. Then we can look into what is meant by mole fraction, molarity and molality. We can take one by one. So we can take what is meant by molarity. Molarity is the number of moles of the solute present in the total number of moles present per million of the. So we have discussed some methods of expressing concentration. The next method of expression concentration, that is a very important method, what is called mole fraction. As the name itself indicates, it is the fraction of the moles of the one component. Fraction of moles of one component present in total number of moles of the total number of moles of all the component. So it is a fraction. It is always be less than 1, so that the total number of mole fractions will be equal to 1. So here we are discussing binary solutions only, that is one solute and one solvent. So when we say mole fraction, we mean mole fraction of either the solute or the solvent. Suppose we are taking the mole fraction of the solute, then in that case number of moles of the solute divided by total number of moles of the solute and solvent. Or generally we can say that mole fraction is the number of moles of one component divided by total number of moles of all the components present in the solution. See, what is mole fraction? See, it is usually expressed by x. Mole fraction is usually expressed by x. If you are going to take the component, say A, mole fraction of the component A is indicated by the symbol XA, such that XA is equal to Na divided by Na plus Nb, where Na is the mole fraction of the component A and Nb is the mole fraction of the component B. So if Na and Nb are the number of moles of A, Na indicates the number of moles of A, not the mole fraction but the number of moles. Na is the number of moles of A, and Nb is the number of moles of B, then XA, the mole fraction of A is equal to Na divided by Na plus Nb. Similarly, see, if I take the ith component, in case of a binary solution, we are having only two components, A and B. Suppose we are having several components ranging from say A to 1 to say I, 1, 2, 3, 4, etc. up to I components are present in a solution. In that case, the mole fraction of the ith component is equal to number of moles of I divided by the number of moles of the first component plus the number of moles of second component plus that of third component and up to the number of moles of the ith component. That is sum of all these number of moles, that is divided by the number of moles of the ith component divided by total number of moles of all the components. That is given by Ni divided by sigma Ni. Sigma Ni indicating the total number of moles of all the components. So that is what is called the mole fraction of the ith component. In I have said in the beginning itself that mole fraction will always be less than 1. It is a fraction. That means the mole fractions of all the components when added together, the sum of all mole fraction will be equal to 1. So that mole fraction will always be less than 1. It is a fraction. This is one of the methods of expressing concentrations and of solutions, and that is a very important method because we are using this in expressing several properties associated with liquids. Now we can discuss a problem to calculate the mole fraction of a solution. See, the problem is this one. One has to calculate the mole fraction of ethylene glycol, that is having the formula C2H6O in a solution containing 31% of ethylene glycol. That is 31% of the ethylene glycol solution. 31%, it is a solution of 31%. Means ethylene glycol is in water. Usually ethylene glycol solution means the solution of ethylene glycol in water. So it is a 31% solution. 31% solution means 31% is constituted by ethylene glycol. With the formula C2H6O means the remaining 69%. So 69% is water. 69% is water. See, as you know, the mole fraction of a component A, XA, is equal to Na divided by Na plus Nb, where Na is the number of moles of the component you are asked to calculate, of which the mole fraction is to be calculated, and Nb is the number of moles of the solvent, or Na plus Nb constitute the total number of moles present in the solution, and Na is the number of moles of the component of which you are asked to calculate the mole fraction. And here Na is the number of moles of ethylene glycol and Nb is the number of moles of water. So in order to calculate the mole fraction of ethylene glycol, you have to calculate the number of moles of ethylene glycol and also the number of moles of water. So number of moles is equal to mass divided by molecular mass. Is equal to number of moles of one component is equal to mass of the component divided by molecular mass. So to calculate the number of moles of ethylene glycol, you have to divide the mass of ethylene glycol divided by the molecular mass of ethylene glycol. See, here it is a 31% solution of ethylene glycol, means if the total mass of the solution is say 100 grams, 31 grams is that of ethylene glycol, 31 grams. So ethylene glycol C2H6O has got a mass of 31 grams, and you have to know the molecular mass of ethylene glycol also to calculate the number of moles. See, for that you have to add up the atomic masses. Here we are having 2 atoms of carbon, 6 atoms of oxygen, and 6 atoms of hydrogen, and 1 atom of oxygen. So the total mass comes to total molecular mass of ethylene glycol C2 H6O is equal to the mass of two atoms of carbon, that is 2 into 12 plus 6 into 1, that is hydrogen, plus 16 is equal to 24 plus 6 plus 16, that comes to 30 plus 46. 30 plus C2, 2 into 12, then H6, 6 into 1 means 1 atom of oxygen, that is 16, so it comes to 30 plus 46, 46 grams. 46 is the molecular mass, not expressed in grams. 46 is the molecular mass. So we are having 31% solution means the mass is 31 grams and the molecular mass is 46. So you can calculate the number of moles. Number of moles is equal to mass divided by molecular mass. So Na, that is the number of moles of ethylene glycol, is equal to 31 divided by 46. 46 is the molecular mass that you can calculate. This is Na. Then Nb is equal to that of water, number of moles of water. Water has got a mass of 69 grams and its molecular mass, as you know, is 18. So 69 divided by 18. This is the number of moles of B, that is number of moles of water. Once you know the number of moles of water and number of moles of the ethylene glycol, you can calculate the mole fraction of first ethylene glycol and then water. But you are all asked to calculate the mole fraction of ethylene glycol only. So you have to calculate the mole fraction of ethylene glycol, that is mole fraction of ethylene glycol is equal to, this is the number of moles of ethylene glycol, that is 31 by 46 divided by number of moles of ethylene glycol plus that of water, that is 31 by 46 plus 69 by 18. So if this is calculated, you will get the number of the mole fraction of ethylene glycol.